and watch it. Thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing today. So without further ado, I'll pass it on to our presenters so that we may start.
Hello, everyone, and welcome back to the Math Happy Hour. So again, we surely appreciate all you guys taking some time to review with us. So today session, we're doing a little different. For those of you who are in your Math 1324, there is a separate link there on your chat for you all to go. Since the classes now are changing topics or they're a little bit different, we want to concentrate on your all's class. So I'll give a couple of seconds for those who are here for Math 1324. Please click on the link located on your chat, please. Very good. So again, welcome. So let's go ahead and get started. So today's topic is standard form of a quadratic equation and graphing. Okay. All right. So first, the standard form of a quadratic equation is given by this ax squared plus bx plus c. And the second format is also a quadratic. And you see, we know that this is a quadratic because our highest exponent is 2. But this form here, we like to call it the vertex form. And I'll explain shortly why we call it that way. Okay. So first, let's look at the general form, right? So the general form of this equation is, again, or function, is ax squared plus bx plus c, okay? The graph of this is a U-shaped curve, which we call the parabola, okay? Now, the one that we have here graphed, we consider this the parent function. So this parent function, from this parent function, we can graph any quadratic function. And it's good to know the parent, because if you know the parent, you'll be able to know all of its children, okay? So a quadratic function is also an example of a polynomial function, okay? And polynomial, as you all may know, poly means many terms, right? Or many numbers. So this has three different terms. It has an x squared term, an x, and a constant, okay? All right. So let's look at some specifics first of the quadratic function. So the general form, again, if our a here is a positive value, okay, our parabola is going to be pointing upward, okay? If our a is negative, okay, it's going to pointing downward. And again, these two forms of the equation are the exact same thing, except they're just in two different styles, okay? This is the general form, and again, we like to call this the vertex form, but these are, in your book, also consider this called the standard form, okay? All right, so let's move forward. And again, please, if you have any questions, let me know, okay? Go ahead and raise your hand or put it on the chat, okay? So again, as I was mentioning, if a is greater than 0 or positive, okay, our parabola is going to be pointing upward. If a is negative, our parabola is going to open downward, okay? So just for review as well, again, all quadratic functions have a domain from negative infinity to positive infinity, okay? It's all the x values. So even though we don't have arrows here pointing, this graph goes forever to the left, goes forever to the right. Same with this one, okay? It goes forever to the left and goes forever to the right. All right, now, so some more specifics on our parabola, okay? On our parabola here, the point here where it changes direction, right? It goes, and it was decreasing function, and then it starts increasing. The point here, this is called our vertex, okay? Now, the vertex here on our parent function is the origin, 0, 0, okay? And you can find the vertex when you have the equation in general form using this formula, okay? To find the x value, you'll get b divided by 2a, and then you multiply it by -1. This will give you the x value of the vertex. And then once you have this value, you plug this value back into the function, and it's going to give you again the y value. Okay, so this is the formula that you would use in order to find the vertex if you're given the quadratic in this form. Now, when it's in this form, in the standard form, again, I like to call it the vertex form, because I can look at this function and just, I can look at this function equation and automatically know what my vertex is, because here the h and k represent my vertex. And we'll see, and I'll show you some examples on how easy we can identify the vertex when it's in standard form. Okay. All right. So another aspect of our quadratic function is that they have what's called an axis of symmetry. Okay. So the axis of symmetry is this imaginary line that we signify with a dashed line, and it goes straight through our vertex. So if you see here, the equation of the axis of vertex of symmetry is actually the x value of the vertex. So if you are able to find the x value of the vertex, you also know the equation of the axis of symmetry. Okay. Again, and when we're graphing, we represent that as a dashed line. Okay. All right. And just as review, we reviewed symmetry before, but it's like a mirror image, right? This is like a y-axis symmetry where it creates the same graph, right? Okay, let's move forward. Okay, so it's convenient to convert from general form to standard form, as you see, if we wanted to graph or find the vertex really easy. Okay, so one of the ways we're going to do that is by factoring. Okay, so we'll review a little bit of our factoring in order for us to do this. So let's go ahead and see an example. Okay, so here, if we have this function, again, in general form, ax squared plus bx plus c, and I don't remember the formula to find the vertex, what we can do is use some of our factoring techniques to convert it from general form to standard form, okay? So the way we do that is by following these steps. The first thing we want to do always, if a is not already 1, we want to make it into 1. We want to factor out an a, but only to the two terms, okay, that have an x. Okay, we leave the constant term alone. Okay, so once we do that, we're going to divide the b term by a, whatever factor we factored out. Okay, so once we have this, we have the b over a. We're going to divide this term by 2 and then square it. Okay, so let's go ahead and continue. So once we square this, okay, this is what we consider our squaring factor. Now, in mathematics, we can't just add any value just because we feel like it or because the teacher told you, right? No, we always want to balance this equation. If you see there's an equal sign, this is also an equation. On top of it's a function, but it's an equation. So we want to balance it always. So if we want to have this factor that we just got that makes our function a perfect square, okay, one way that I can add it without affecting it is if I add it and also subtract it. So if I add it and also subtract it, what I'm really adding is 0, right? I'm not changing the function, but this is what's called balancing. Now, if this was a true equation, some of you might recall that if you add something on the right, you would add it on the left. And that's why it's negative, because think of it like this. Think of it as if I added b over 2a squared on the other side, but I moved it on this side. So if this was positive on this side is now negative again, but I'm really adding 0, okay? So once I've done this, okay, I only want to borrow the positive one. I want to borrow the one that made this part a perfect square. Okay, so I would take it out of the parentheses, and if I take it out of the parentheses, I need to give back the a that I had factored out originally. So this is again the example. I'm going to multiply a times that negative b over 2a squared. Okay, so once that I've done that, again, I have a constant that's outside. I would add these terms together. Now this term, what we just did, the example that I just provided, is something called completing the square. I had a equation that just had two x's, and I was missing the squaring term, and I found it by this formula, b over 2a squared. Okay, so this term here, okay, if I were to factor out and solve it for you, it's going to be this term here. Again, this is why it's called a perfect square, because what I would have is x plus b over 2a squared. Okay, again, this plus c minus a over 2a squared, we would combine this term. And by doing this, we would have now we've converted the equation from general form to standard form, where our x value, which was given to you at the beginning, is negative b over 2a, and our y value is this, c minus a times the b over 2a squared. Okay? So the best way to see something like this is with an example. So let's go ahead and look at this example. You have homework problems that say, write the quadratic function in standard form and identify the vertex and its axis of symmetry. Okay, so the axis of symmetry is going to be very easy. Like before, it's just if we know the x value of the vertex, we know the axis of symmetry as well. Okay, so you see that we are given a function in general form. It's ax squared plus bx plus c. My a value here is 1, my b value is 2, my c value is 1. So if you see here, we don't have to factor out anything already because our a is already 1, so we don't need to factor that. So, but we do want to isolate just this part, the x squared plus 2x. Let's find out what is the plus c value that would make this a perfect square. So let's go ahead and use the formula that I just showed you, okay? And again, it's really not a formula, it's a factoring technique, right? So I'm gonna grab half of b, and then I'm gonna square it. So again, b in my case is 2. I'm gonna divide that by 2, which is gonna give me 1. And when I square 1, that is a 1. So I need a 1 here for this to be a perfect square, but I already have a 1 there, so I don't have to add anything, right? Or just for practice purposes, just so you know that, and you can see that I'm really not adding anything when I add a plus 1 and a minus 1. This is what I needed. I needed a 1, but I'm going to subtract a 1. And when 1 minus 1, that's going to give me 0, right? But again, I know that that I have a 1 here already, so I can go ahead and just complete my square, right? So completing the square again, the plus 1 minus 1 is going to cancel, just again, in case that I did have to add it or subtract it, and this plus 1 was a different number, and you can see I get 0 out here, okay? It didn't affect it at all, does not affect my equation. But I know this, if you don't see it or recognize it, you can go ahead and FOIL it. X times x is the x squared, then x times 1 is x, the 1 times x is x. It's going to give me 2x, and the 1 times 1 is 1. So this gives me a perfect square. I have 2 of this, x plus 1 times x plus 1, which simplifies to just x plus 1 squared. So hopefully we can see that. Now I can see what my vertex is, right? So my vertex in this problem is negative 1. And again, there's no plus value here or value out here. So my my k is 0, right? So here my vertex is at negative 1, 0. And the equation of my axis of symmetry, again, is the x value. So x equals negative 1. That axis of symmetry will always go through the vertex. Okay. Any questions? All right, let's look at another example then. So this one, as we can see, a is not 1. So it says, write the quadratic function in standard form and identify the vertex and axis of symmetry. So the first thing that I need to do is I need to factor out that 2. Okay, so I'm going to factor out that 2. So when I do that, okay, I get 2. I'm factoring out the 2. 2 times x squared is going to give me the 2x squared. 2 times the 4x is going to give me the 8x. And I'm missing the squaring factor. I'm missing that plus c value, right? And then outside, I leave the constant, plus 7. Okay, so now what I'm going to do is I'm going to apply the equation or the factoring technique to find my perfect square value, right? So I'm going to grab b, which is 4, divided by 2, and square it. 4 divided by 2 is 2, and 2 squared is 4. So what I would do, again, to balance the equation, I want to add 4, but I'm also going to subtract 4. But the only one that I need is a positive 4. So again, I'm going to take that negative 4 outside the parentheses and give back the 2 that I had factored out originally. Okay, so when I take the negative 4 out, negative 4 times 2 is a negative 8. And inside the parentheses gives me this x squared plus 4x plus 4, which I know is, I just have to look at this value here. It's going to be x plus 2 squared, right? So my, if I had to FOIL it, or again, just to show you my work, this signifies x plus 2 times x plus 2, and then the minus 8 plus 7 gives me a negative 1. And I know that because this is two identical terms, can combine this into x plus 2 squared, okay, minus 1. So I've converted from general form into standard form. And now it's very easy to see that the vertex is at -2, -1. Now, again, just as review, we did this last week, but why is it a -2 if we see a +2? Remember, also think of if you were finding the x-intercept. If you wanted to find the x-intercept, you set y equals to 0. So I need to move that 2 to the other side in order for me to find out what x is. So if it's a +2, I need to move it to the other side to solve for x. That's going to become a -2. So that's why the x value is a -2. Okay, so my vertex is at -2, -1. This graph shifted 2 units to the left, 1 unit down, and the axis of symmetry, again, is the x value of the vertex. X equals -2.
Mr. Carizales, can I add something really quick?
Yes, ma'am, please, go ahead.
Okay. So one of the trick, I guess you could call it a trick, is whenever you take half of b, so in this case, b was 4. If you take half of it, you got the 2. Whatever you get for the half, that's always going to be the number that you're using here. So since we had half of +4 is a +2. If you had a -6 here, then you would enter a -3 and a -3. So just a little shortcut that maybe some of you already picked up when you do the examples. Go ahead.
Excellent. Thank you for that shortcut, Ms. Chuka. All right. Let's do one more example here. Okay, write the quadratic function in standard form and identify the vertex and axis of symmetry. So I see here that my a is not 1, so I want to factor out that 5. So that's the first thing that I will do. I'm going to factor out the 5 from just the terms that have the x, and again, I'm going to leave the constant outside my parentheses. So let's go ahead and factor out that 5. 5 times x squared gives me the 5x squared. 5 times 3 gives me that 15x. Okay, so now again, as Ms. Chuka pointed out, here is the other tall tale sign, or the shortcut to find out what's the perfect square value, right? See, before I squared, I have this value 3/2. Okay, so that's my perfect square. That's the one that's going to be x plus 3/2 times x plus 3/2. Okay, so again, another little piece of easy advice, right? So, but this is our formula. We're going to take b divided by 2 and square it. So 3/2 squared, that's 3 squared is 9, 2 squared is 4, so we have 9/4. So I want to add a 9/4 and also subtract a 9/4, okay? I'm basically adding 0. I'm not adding or taking away to this equation. I'm not changing it. All right, so I want to only borrow, okay? I want to borrow just the positive 9/4. And by me just borrowing the 9/4, I want to take the negative 9/4 outside the parentheses. So that means I have to give back the 5 to the negative 9/4 that I take out, yes? So when I do that, okay, I have the positive 9/4 inside. I have the negative 5 outside. And then when I multiply 5 times 9, that's 45, right? So it's a negative 45 over 4, okay? All right, so again, we have this, but we know what this perfect square is, right? This value is going to be the x plus 3/2 times x plus 3/2. Like, again, the one that Ms. Chuka had mentioned before, and that is also right here that we use to calculate that perfect square value, right? So I know that this converts into just 5 times x plus 3/2 squares, and the outside is just combining the like terms. So what I did is I converted the 5 into a fraction, because in order for me to add fractions, I need to have a common denominator. So 20 divided by 4 gives me, or negative 20 divided by 4 gives me that negative 5. So now I can add these two fractions. So a negative 20 minus a negative 45 is a negative 65. And again, I keep my common denominator, which gives me negative 65 over 4. So my vertex, again, is at negative 3/2 for the x value and negative 65 over 4 for the y value. My equation of the axis of symmetry is always the x value of the vertex, x equals negative 3/2. And again, I also want to remind you, when graphing on your computer on the WebAssign, you have to indicate this axis of symmetry, this vertical line, as a dashed line. Okay, very common mistake students do is they do a solid line and the computer marks it wrong. It's like, why did it mark it wrong? Well, because that line needed to be dashed. Okay, so be very careful when inputting in the computer. Any questions so far? Right, very good. All right, so just as a recap, as far as completing the square, um, whenever we have this form, ax squared plus bx plus c, again, we always, if a is not 1, we want to factor it out, and we'll get b and divide it by 2. Okay, and again, if we factor it out in a, it would be 2a. Okay, so again, this is just a quick review as far as just we did. We have to substitute our values, simplify, add our outside constants, and then simplify once more to have our vertex. Okay. All right, so our parabola, if we were to see here, okay, if it says write the standard form of the quadratic function whose graph is this parabola shown. So the first thing we see that if we remember, our parent function that we just talked about right now is here, right? I'm sorry for the messiness. Okay, so my vertex was originally at 0, 0. But what I see on this parabola here that is in red, I see that from my parent, it got shifted 1 unit to the left and 1 unit down, which gave me this vertex, negative 1, negative 1. So I know how to do that, right? If I can write this in standard form and show that this is my h and k, right? My h becomes a positive 1 and my k is a negative 1. And I'll show you why it's a positive 1, right? So this is our equation for the standard form, a times x minus h squared plus k, where my vertex is h and k. So if I have these points, okay, negative 1, negative 1, if h is negative 1 here, a negative times a negative is going to give me that positive, right? So again, and then the k, the value here is directly to the negative 1, right? So it's just plugging in this information to the standard form in order to get our vertex. So once I do this, again, I am plugging in the values. The a, which I don't, is not given here, it's not shown, so I'll just leave it as the variable a. I have 0 minus the minus 1 squared, the minus 1, right? So when I add these, actually, sorry, this is, and I'm using 0 from my vertex, right? From my a point that's going through the graph, right? So here, I'm able to also calculate a, right? I used a point on the graph to calculate my a value, okay? And which gave me a is equal to 1. So my answer is just x plus 1 squared minus 1. Okay? So let's do another example. Let's go through another example to show this again. Let's say that they're giving me the equation, okay? That is, or the vertex, excuse me, negative 3, negative 15, but I want this parabola to go through this point, 0, 3, right? So I have all the values, just like the example before. This is my h, this is the k that's given to me. I just need to have one value in order to come up with my whole equation. And the point that they're giving me is an x value for 0 and a y value for 3. So let's just go ahead and plug in, right? So here we have y is equal to 3. And remember, f of x replaced our y variable to indicate that it's a function, no longer an equation. 3 is equal to a is the variable that we're about to solve. Again, x is 0 again, minus -3, that's what h is, squared, minus 15. This is the value for k. Let's go ahead and simplify. So we have a negative times a negative is a positive. So we have 0 plus 3 squared minus 15. So 0 plus 3 is just 3 squared minus 15. So 3 squared is 9. Give me a9 is equal to 15. I'm going to add 15 on both sides. 15 plus 3 is 18. And to solve for a, I'm going to divide both sides by 9. So 18 divided by 9 is 2. So my equation in standard form, okay, is 2 times x plus 3 squared minus 15. And again, this information I used to find my a value, but if I could have started right off the bat, because they gave me the vertex, I know that this graph is going to move 3 units to the right here, excuse me, to the left, but it's be indicating as with a plus 3, and then the negative 15 is just my k value inside. But I used this point in order to find my a value, okay? All right. So if we wanted to find the intercepts, again, intercepts means the zeros of the graphs. That means that when the y value is equal to 0, right? So if you also been noticing, it's going to be very easy for us to find the zeros of the graph if they're given in standard form. Because in general form, we may have to either use the quadratic equation or factor. Okay, but if they're giving the equation in standard form, it'll be very easy and use algebra just to find these zeros. Okay, so the zeros of a graph are the root solutions when y is equal to 0. Okay, and we just solve for x. So let's look at some procedures as far as to do that I just spoke about. Okay, so one way is to use the square root property. And again, we can only use this one when they give the equation in standard form. So we can't always use it because they don't always give us the equations in standard form. Factoring, sometimes it may be difficult to do, or it won't be able to do it if they give it to us also in standard form. Now, the quadratic formula you can always use, no matter how they use it. As long as you identify A, B, and C, your quadratic formula will always work. Now, I love the quadratic formula, but again, it's a long formula. Some of you guys might remember it from back in your high school days. And I think it's nice because you can always use it, but sometimes the square root property or the factoring is much easier than the quadratic, but it's up to you as far as what option you want to use and what's best for you. Okay, so let's go ahead and look at an example. So if I have a function here given x squared minus 4, right, Ms. Chuka? Factoring is always the way to go, right? So if I wanted to solve for x, I can solve for x, and I'm going to use my square root property, because when I add 4 on both sides, it's going to give me 4 is equal to x squared, and my square root property means that I can take the square root of both sides, and when I do that, x is going to be plus or minus 2. So my two x-intercepts for this parabola is that x equals 2 and x equals negative 2. Now, as I mentioned to you before, if they give us the function in standard form, we could also apply the square root property by solving for x. Again, we replace the f of x with the y, and again, y would be equal to 0, and then just solve for x. We're going to add 27 on both sides, divide by 3 on both sides, take the square root of both sides. The square root of 9 is going to give me plus or minus 3 equals to x minus 4. So I'll add 4 on both sides. So 4 plus 3 equals 7. That's one of my x-intercepts. And 4 minus 3 equals 1. That's my other x-intercept for this given function. Again, and these are examples of using the square root property. We can also factor, right? Whenever they give us a simple trinomial or polynomial in this form where my a is 1, I can factor this, right? I can say to myself, I need two numbers that when I multiply them together give me -6, and when I add them together give me -1. Well, what are those two numbers? -3 and a +2. A -3 times a +2 gives me a -6, and -3 plus 2 gives me a -1. That's right here. So this x squared minus x minus 6 equals to 0 can factor into x minus 3 times x plus 2. And then I just use my 0 property that when I multiply two numbers together, either this one is 0, this one is 0, or both of them are 0, right? So if I don't see the x-intercepts, set them equal to 0. X minus 3 is equal to 0, and or x plus 2 is equal to 0. So when I solve for x on this one, x is equal to 3, x is equal to -2. And these are my x-intercepts for this quadratic equation. Okay. Now, talking about the quadratic formula. Again, the quadratic formula is beautiful formula, right? Always works. It'll always give you those x-intercepts. But as you can see, it's a messy formula, right? And you have to be very careful when plugging it into your calculator. You got to make sure you use the correct parentheses, to indicate the correct order of operations. But for review, for all of those who want to use a quadratic formula and don't remember the formula is given by this: -b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so again, if I have this function, my a here is 1, my b is -2, my c is -8. I plug my quadratic equation, and look, I get the same answer as before. But I don't know about you guys, but this side looks a lot simpler than this side. And then on top of that, depending on your teacher, they might have you memorize this formula. They might not give it to you on a test. So again, the factoring, you could always fall back on that. Okay, it's much easier work. All right, so let's move on to section 2.2. Ms. Chuka, would you like to jump in?
Yes, thank you, Mr. Carizales. So section 2.2 is going to be kind of a continuation of 2.1, but we're going to get into more details about some characteristics of the graphs. And so the first thing is we're looking at polynomials that have a degree higher than 2, for example. We might have a degree of 3, 4, 5, and so on. So what is a polynomial? First, a polynomial is a continuous graph, as you can see here on the left side. If you have a break in the graph, then this is not going to be representing a polynomial. And then the other characteristic of a polynomial is that the curve is a smooth curve, so you don't have any sharp edges. Okay, so one of the first characteristics that we need in order to graph a polynomial is to understand the end behavior. In other words, we want to know what is happening to the graph on the left side and what is happening on the right side. So in your textbook, you have a lot of different rules, but I figure that having a visual is always much better, at least for me. And so if some students are more visual. So what I like to tell my students is if you understand these 4 graphs, you'll always remember what the rules are. Okay, so this is the graph of x squared. And as you can see, x squared on the left side here, it's rising to the left and it's rising to the right. Now for this one, the equation is -x squared, and we say that it's falling to the left and falling to the right. And then we have the x cubed, which is rising to the right and falling to the left. And then the -x cubed is rising to the left and falling to the right. So in order to use the leading coefficient test, you need 2 things. You need to know what the degree is, and you need to know what the leading coefficient is. The degree of a polynomial is the term with the highest exponent. So in this case, the highest exponent that I have here is just 2, and the number 2 is even. And the leading coefficient is the number in front of that term, which is going to be 1 in this case, and 1 is positive. So if you have a graph that has an even degree and has a positive leading coefficient, the end behavior is always going to rise right and rise left. If you have a polynomial that has a degree that is even, but the leading coefficient is negative, then the behavior will always act like this one here, where it falls right and falls left. If your degree, this should say 3, if your degree is, in this case is 3, is odd, then, and your leading coefficient is positive, the behavior is going to rise to the right and fall to the left. And then on this side, the degree is 3 also, which is odd. And so what that means is that if you have an odd and it's negative, it's going to rise to the left and fall to the right. And so how can we use these graphs? Let me give you an example. So one of the questions on WebAssign that you'll be seeing is to describe the left hand and right hand behavior. And so if we look at this polynomial, the first one, you need to get the, and if you have these 4 pictures in your mind of what they do, then we can use that to help answer this question. The degree here is 8 because 8 is the largest power that we see, and the leading coefficient is 3. So notice that 8 is even and 3 is positive. And so is it going to behave like my first graph, second graph, third graph, or fourth graph? So we will look at when it's even and positive, which is going to be like this first one. So my answer would just be that the graph will rise to the right and rise to the left. Okay, so let's try the second one. Take a minute and ask yourself, what is the degree and what is my leading coefficient? And then is it going to act like the first graph, second graph, third graph? Okay, so let's just do the degree together. The degree is odd and the leading coefficient is negative. So you have 3 and negative. And so in the chat, if you want, you can press 1 for the first graph, 2 for the second, 3 for the third, or 4 for the fourth one, whichever one you think it's going to behave like. Okay, so we're putting 4, and that is correct since the degree is odd and the leading coefficient is negative. Then we can say that this graph is going to behave like this graph here. So the answer that you're going to select on your homework in WebAssign, they give you multiple choice. So you would pick the one that says the graph will rise to the left and fall to the right. Okay. So let's go to the letter C. So here we can see that the degree, if some of you put 6, then it would be incorrect, right? Because your degree is not always the first term. It's going to be the highest exponent, in this case 8. And the leading coefficient is not the first term. In this case, it's going to be a -4. So ignore my 3 here. It should be -4. Okay, so this graph is going to behave as this one here. So we would say that the graph falls to the right and falls to the left. Any questions on letter C? Okay, what about letter D? What is the degree of that polynomial? What do you guys think? So the degree here is going to be 3, right? And the leading coefficient is not a 1, okay? Notice here that we have a -2 on the outside. We're going to have to distribute that into the parentheses. And when we do that, -2 times x cubed is going to give me a leading coefficient of a -2. So if my degree is odd and it's a negative coefficient, then we're behaving like the last one again. So the graph will rise to the left and fall to the right. Now, why do we want to know this information? What all this is leading to is, can we sketch the graph of these functions, okay? And we're gonna put everything together in the sections. So another important characteristic is understanding when a graph is going to cross a 0. So notice here the graph is crossing the x-axis, or when it's gonna touch and turn. So if you look at these 3 graphs, can anybody guess when the graph is going to cross or when it's going to touch, and maybe what is it in the what is causing that to happen, basically. And so we can look at these zeros carefully, right? So here I have a -1, a 2, and a 4. So these are all my zeros. And then this one I have a -2, which is right here. I have a +2, which is here, and a -2, which is also here. So when they duplicate, so notice here I have a -2, and then I have a +2, but notice that 0 is listed here twice. And when it's listed twice, it touches and then it turns. Okay, so if a 0 repeats an even number of times, it's always going to touch and turn. If it repeats an odd number of times, then it's just going to cross. Okay, and we'll look at that a little bit more closely here. So to help us remember those rules, I always think about x squared and x cubed, because I know what those graphs look like. So if I forget the rules, if I think of these two guys, then I can they'll help me remember what the rules are. So if we have f of x equals x squared, and I want to find the 0, I would set this 0 equals to x squared. And do you agree that x squared is the same as x times x? And so I can separate this as 0 is equal to x and 0 is equal to x. So I have two zeros. It just happens that they're the same. So since the 0 appears twice, that is why the graph touches it and then it turns. If we look at the x cubed, I can write it as x times x times x, which in turn will give me x equals 0 3 times. Okay, so x equals 0 occurs 3 times, which is an odd number of times, and therefore you can see that the graph is going to go right through it. Okay, so it's not going to touch and turn. Instead, it's going to go through it. So let's do an example here. So it says find all the real zeros and determine the multiplicity of each 0. So multiplicity, let me go back over here. Multiplicity is just how many times does this 0 appear, okay? So if we want to find the zeros, remember that your first step is to set the y equal to 0 and then choose a method. So for me, I always like to check factoring first, but I always have to tell myself if I can't factor in less than a minute, then maybe it's not factorable and maybe I need to use the quadratic formula. But in this case, we can't factor. It's going to be x minus 1, x minus 1. So then I can use the zero product property, which tells me that x minus 1 is equal to 0 and x minus 1 is equal to 0. If I solve for x here and I add 1, I get 1 is equal to x and 1 is equal to x. So x equals 1 is my zeros, right? And they appear twice. So since x equals 1 appeared twice, that's an even multiplicity. And so the graph is going to actually come to the 1, touch it, and then it's going to turn. Okay. So in the computer, you would enter that the multiplicity of x equals 1 is 2, and that the graph is going to touch and turn. Okay, let's try another example. Find all the real zeros and determine the multiplicity of each 0. So here, again, since they're wanting us to find the zeros, we set f of x equal to 0. And notice that they all have at least one t. So we can factor out a t here. I think I made a mistake here. Let me see. Okay, let me cross out that equation right here. Let me get my pencil. Give me a quick second. So this is not the right equation. We're looking at this equation, okay? So notice that they each have a t squared in common, right? So we can factor out a t squared. So t squared times t squared gives me t to the 4th. T squared times negative t gives me a negative t cubed. And t squared times negative 30 gives me a negative 30t squared. So if you notice, what we have left in here is quadratic, so I can factor, or I can use a quadratic formula. So let's go ahead and factor it. T squared minus t minus 30 factors as t minus 6 times t plus 5. And then, of course, we have the t squared here. So by the zero product property, I can separate those as t squared equals 0, t minus 6 equals 0, and t plus 5 equals 0. So if I solve for t, this one would give me, if I take the square root, would give me t equals 0. And this one will give me a t equals 6. And if I subtract 5, I get a negative 5 equals to t. So if you notice here, the 0 at t equals 0 actually occurs twice. Although I only wrote it one time, this right here is appearing twice because if you remember, let me just rewrite it as, I can rewrite this as t times t, which is going to be t equals 0 and t equals 0. So one of the common mistakes that I see people do is they take the square root here and forget that there's another 0 here. Okay, so since it occurs in even twice, that's an even multiplicity. So we say the multiplicity of t equals 0 is 2, and the multiplicity of t equals 6 and t equals negative 5 is going to be 1 because they both appear only one time. Okay, so at t equals 6 and at t equals negative 5, the graph is going to cross, and at t equals 0, the graph is going to touch, and it's going to turn. And so I graphed it for you here so you could see. At t equals 0, the graph touches and it turns. At t equals negative 5, it goes through it. And at t equals 6, it goes through it. And you can't see the rest of the graph because it goes all the way down to like negative 300 or something like that. But I just wanted you to see the behavior that it's doing here in the zeros, okay? And we could actually see the behavior here too. The degree is even, there's a positive coefficient. So this graph is going rising to the right and it's rising to the left, okay? So how can we put all of that together to form a graph, okay? So we're gonna form a graph here. So in order to graph this, you need to be able to do these 4 things. Identify the end behavior, find the zeros and the multiplicity, and whether it touches the turns or crosses, and then the y-intercept, and then additional points to help you fill in the gaps. Okay, so we'll do the behavior first. So my behavior here, I have an odd degree with a positive leading coefficient. So that means that my graph will rise to the right and fall to the left. Okay. Find the zeros and identify the multiplicity of each 0. So in order to find the zeros, I let g of x equal to 0 here. They both have an x squared in common, so I'm going to factor out my x squared. X squared times x is x cubed. X squared times 3 is negative 3x squared. I can set this equal to 0, so I get x squared equal to 0, and x minus 3 equal to 0. If I solve for x, I get x equals 0 and x equals 3. While x equals 0, don't forget, since this is squared, that means you have 2x equals 0. So the multiplicity is even, so the graph is going to touch and turn. And then the x equals 3 is odd, so the graph is going to cross. Okay, and then we'll put this together in a second. To find the y-intercept, we let x equals 0. So anywhere you see an x, we're going to replace it with 0. And so if I replace x with 0, then I just get 0. So my y-intercept is 0, 0. Now I can take all of this information, and the first thing I'm going to do is plot my zeros and the y-intercept. So my zeros are x equals 0 and x equals 3, and then I have my y-intercept of 0, 0. So I only have 2 points to help me. My second step is apply the end behavior and the multiplicity. So the end behavior says that the graph is going to rise to the right And I encourage you to use a pencil when you're doing this because sometimes you have to adjust your graph a little bit. But since it's going to rise to the right at this 0, I'm going to put an arrow going up, and then it's going to fall to the left. So at this 0, I'm going to put an arrow coming down. And then the multiplicity, it tells me that at x equals 0, the graph is going to touch. So I'm just going to touch and turn here, so you could barely see my arrow here. And then for 3, it's going to cross. So I have my whole line crossing through here. But I don't know what's going to happen down here. And so that's where additional points will be helpful. So I'm going to plot f of 1. So anywhere I see an x, I'm going to substitute a 1. So I get a 1 squared minus 3 times 1 squared. That gives me a negative 2. And then I'm also going to do 2. So f of 2 is 2 cubed minus 3 times 2 squared gives me a negative 4. And that might be good enough for some of us. But if you're really curious, you can do between 2 and 3, like a 2.5. And you can see that's going to be a negative 3.125. Well, if I plot those points, here are the 3 points that I just found, then I can sketch my graph. And so my graph will look something like this. Okay. And so I'm going to show you the graph that the computer did so that we can compare it to my pretty sketch. So of course the graph is on the computer is always prettier, right? But you can see here we have the same point. So negative 4 is right here, and then you have your 2 zeros, and then you have this point here. Okay, so picking additional points can be very helpful so that you know exactly when you have to start turning back up to your other 0. Okay, so in order to graph, you do have to know the end behavior and the multiplicity of the graphs. Okay, so you have to know this and this. So today when we found the zeros, it was a little bit, it wasn't as difficult because they had a greatest common factor in common, and we were able to solve for x. Now in the next section, 2.3, you're going to start to run into polynomials that are a little bit more difficult to find a 0. And so in the next session, we're going to be going over some of those examples and some of those strategies that you can use so that you can solve for these zeros. Okay, so we hope to see you next week. And if you have any questions, we'll be here for a few minutes, and I'll pass it over to Peter.
Thank you, Ms. Chupa, and thank you, Mr. Rosales, for today's presentation. I posted the link for the previously recorded sessions and a survey to help us improve. And make sure to sign in. That's the last link. That's for your attendance. And the code word is excited.